Hello, everybody, and welcome to the Bungalows for Bachelors late night learning. Today, we are going to be talking about custom carpentry. And by that, I mean the ability to look at something you got to do in your house and be like, hey, you got to frame a soffit, or hey, you got to fur that down or fur that out, or you got to do something that's just not studs, headers, and walls and ceiling joists, right? So the premise here is, can you learn how to do custom carpentry, right? So that's what we're going to talk about. So, getting into it here, first thing is, let's see, if you want to learn about construction from an engineering perspective, or from, the I want to know how to do it myself perspective, then you can go ahead and check out my school server with the link in the description that I'm going to put in there, and later I will comment it and you can check it out there. Basically, I've got a home design program if you want to see generally how a home is built. And then I've got a framing design program if you want to see how all the framing is thought out and put together, if you like to know about how to build the thing itself. So, that said, we're going to get right into it here. So, what do we need to know about custom carpentry? Also, we got Mr. Jonathan in the chat here. Thank you for showing up, Mr. Jonathan. Glad to have you. I appreciate your presence here, and I hope you learned something from this fantastical experience. So, first thing we want to talk about here is going to be directions of strength. All right. So, if you were to look up the, you know what? I'm probably not going to get in trouble for doing this, but these books here, the NDS standards, National Design Specifications for Wood Construction, there's a whole bunch of tables and stuff in here, and the tables have lots and lots of charts and columns and rows and stuff. And sometimes it's not very obvious what numbers you need for figuring out like your framing situation. So, directions of strength. So, when you are going to stress a member, a wood block in this scenario, there are different strengths in different directions because wood is not a homogeneous material like a steel, right? Like a metal, or maybe like crystalline materials or other things like that. So, because wood is not homogeneous, it's going to have different properties in different directions. So if you took a wood block and you pulled on it and it was some cross-sectional area or whatever, right? You're going to get some species of wood. You're going to get some like net force you can put on this, right? So you can put like 1,000 pounds of tension on that wood block or whatever before it actually like breaks in half and just shatters. So that would just be regular tension. If we were to take the same wood block and we were to add compression, there is a different number for that. And that's just because of the way it is, right? So compression is a little more complicated because we're also going to deal with buckling in that scenario, and that is going to introduce some other factors, but that's just one way. Now, just talking about tension here. So tension in this case is called, this would be tension, presuming this is like the stick of like, presuming we're cutting blocks out of like 2x4s and stuff, right? When we saw lumber, we saw it down the length of the tree. We don't make lumber, circles. So typically the grain is always doing this, right? The grain is always parallel with the length of the thing that you have. So if you have tension in this direction, what you have is you have tension parallel to grain. And there are little numbers and symbols and things that represent that. So when you're looking through the charts and you need to know what is southern yellow pine number 2 grade at, what is that tension parallel to grain strength going to be in pounds per square inch? That's where we get those numbers from the table and everything. So that changes depending on how you apply the stress in relation to the grain direction. So in this case, this is parallel to grain. There's basically parallel to grain and perpendicular to grain. And basically what's going to happen here is if I turn this flat. Now it's the same block, but now it's flat. All right, so that would be parallel to grain. You can apply stresses perpendicular to grain, and basically that's a big no. You don't want to do that. Um, so let's see. Think about that. Yeah. So perpendicular to grain stresses would basically be like this. So if you, for whatever reason, had some scenario where your board was trying to be pulled from this face and this face, and you're trying to split the board open, you would have a very high likelihood of failure because this is called cross grain tension. And it is effectively like wood is ridiculously weak in cross grain tension. If you ever seen a piece of wood like this and it's got like a little splinter started up here on the side, and you're like, oh, I don't like that splinter. It's sticking out. I don't want to get poked while I'm framing. I'm just going to peel it off. Well, when your act of peeling it off is inducing that cross grain tension, which is why it's so easy to rip that piece of wood off, even if it's like a solid chunk of wood. Okay. So that's cross grain tension. We want to avoid that at all costs because it's like we don't even attribute any strength to it. Like we would never want to introduce a loading scenario like that. And so will you ask, well, how is this possibly going to happen in a loading scenario? And I will give you an example. So what's going to happen is sometimes wood connections get complicated and we use big bolts and things like that. And let's say that we had some connection where, let me think about this real quick. Yeah, let's do this. Okay, so we have a wood member, or no, let's make it a cable because we're going to get cool materials here. All right, so there's a cable hanging from the ceiling, and the cable comes down, and there's like a, what is going on with my marker here? There we go. So there's going to be this bolt here, and I've got a beam sitting on a wall over here, pretending this is some cool architectural feature, right? There's our beam. And instead of doing anything over here, we're going to hold the end of the beam up by putting a bolt through it. And this bolt, this beam is, pretend the beam is proportional, right? So if we support the beam here, and let's say all of our ceiling was going to suspend from this beam for whatever reason, a bunch of cross-sectional ceiling joists, right? So all the weight was physically connected to the bottom of the piece of wood, and the support holding the beam up is connected to right here. Then what's happening is in this zone right here, zooming in, we have the bottom of the beam being pulled down by the ceiling joists, and then up here is a bolt trying to pull the beam up. So this area of the beam is actually trying to be split open, cross grain tension, and that is very, very bad. Now, that's tension. That's pretty much the things to think about. I mean, most of the time, tension's not going to be the limiting factor, like unless you're trying to avoid that. Now, compression is a little bit different. I'm going to let that fall. Compression parallel to grain is typically the strongest. And that makes sense because if we grow trees vertically and the trees are heavy, they're going to want to support their own weight, right? So when you add weight to the tree after it's been cut into a little thing, it's going to have a lot of compression strength naturally because that's just what the material is designed to do. So that's compression parallel to grain. Now, compression perpendicular to grain is basically going to be, you're going to risk crushing. And when I say crushing, I mean, hey, my cat's playing with the eraser. When I say crushing, basically what that's going to mean is, let's say you had a wall plate right here, double top plate, and you got studs over here, and you're going to put a beam right here. You're going to set a beam on top of this wall. That's a cross section of the beam. Now, what you're concerned about here, and like rarely is it a problem because typically when beams get really big, they also get wider. And the wider it is, if we're looking at that spot right there, top down, then this would be the beam going out into the room. And there's our top plate, right? So this area right here, that is the bearing area of the beam on the wall, presuming that the wall is flat and the beam is flat and there's no funky cuts or anything. Right. So presuming you have all that bearing area, you're good. Now, the reason this is usually not a problem is because really heavy loads sitting on the wall can actually crush the wood. And what that means is the wood is getting squished perpendicular to its grain direction right here, and it's somewhat weak in that direction. And so what's happening is the beam will actually sink into the wall plate if it's too much. It's way too much weight, right? That's bad. That's crushing, and that changes how everything like the break sheetrock. That's a problem. So we don't want to do that. But that's typically not a problem because as this load increases, theoretically, like the beam's carrying more weight, it's a bigger span beam, then the beam width will also increase because the cross section of the beam has to increase to accommodate all this extra weight. And so that area is going to increase and it's not going to be an issue because as that area increases, it spreads out the load over the wall more and you're fine. Where this becomes an issue sometimes is where you have super concentrated loads coming down through your house in a post, and the post is going to connect to the block, and the block is going to connect to something below it, and that's going to hit like a header, and the header is going to hit some jacks or something, right? So you got to track those loads down through the structure if you've got something complicated. And that's where you can actually get significant concentrated loads over small areas, and you got to watch out for that because you can easily crush perpendicular to grain. So that said, that's the directions of strength thing, right? So wood is going to behave differently when you load it in different directions. Now, why the heck am I talking about that? Well, I'm talking about that because framing is all about structure. It's all about like you're putting things together that are designed to hold other things, and those other things are going to have some weight to them, especially if we're talking about the actual walls and stuff like that, right? So it matters. But in terms of maybe a soffit or some custom like feature that you want to do this cool shape coming off your ceiling, but it's like going to hold some drywall, it's going to have angles, and you just want to know how to like connect your framing back to your walls such that you know it's not going to like shift or move later on. It's going to be nice and strong. So we're going to talk about connections next because connections are the next most important thing. So presuming that you understand somewhat about how the wood itself can be loaded and is ideally loaded, then like for the small block stuff we're talking about, these like all that tension and compression stuff, that's just not going to matter because you're not going to get crazy weights on anything. The walls and the ceiling joists and the beams and stuff, that's where the real weight's happening. So not a huge deal. But connections are going to be made with usually either nails or screws. And we're going to talk a little bit about the difference, right? So nails are a ductile iron, steel, and screws are usually a higher strength but more brittle steel. And what we're going to talk about is the amazing stress strain curve. Oh boy. I don't remember the letters. I think strain was like tau or something. And stress was something else. Okay, this is stress. This is ouchies. This is how much pain are you feeling? How much force is being applied, right, over area? And this is effectively like think of it as deflection or deformation. So if I take a rubber band, for example, I'll get some colors here. So red's going to be for rubber band. R is rubber band. Okay, so if I take a rubber band and I start pulling on it super lightly, it's going to start stretching a lot, right? So I barely have to pull on it at all, and it's going to stretch out because that's what it does. So it's going to look something like this. It's going to have a super low curve like this, and it's probably just going to go up like that forever. I mean, not forever, but eventually rubber bands break, but that's going to be super low, right? Now, if I take just a thicker rubber band, really, if I take a much thicker, heavier rubber band and I start pulling on it, I'm going to have to pull a lot harder to get it to stretch farther, right? So what's going to happen is as I'm increasing the force, it's going to look something like this. And my headset likes to turn off sometimes randomly. Turn it back on. So it's going to look something like this because as I increase my stress, did I draw these backwards? Hold on. No, I didn't. So for a small amount of stress, no, I did draw them backwards. My bad. For a small amount of, this is supposed to be the light rubber band. L for light rubber band and H for heavy rubber band. As I have a small amount of stress, I pull a little bit, I get a lot of strain. This is the strain. This is the deformation part, right? This is the delta X in length. Okay. So if I so that's how the stress strain curve works, right? So if I take a steel rod and I pull on it, you could imagine how hard you'd have to pull to get the steel rod to stretch out. Now, most people think, well, how a steel rod wouldn't stretch out? It's freaking steel. However, in large loads and circumstances that are, where you've got big stuff going on, all materials deflect. It's just a matter of how much. So, like, if we compared steel to these rubber bands over here, then it would it wouldn't even see the line. It would basically be like down here somewhere, right? So you're going to put a lot of stress on it, and you're hardly going to get any deflection out of it. Now, that's compared to rubber bands. If we're going to forget about rubber bands, what we're going to do is we are going to talk about steel, right? Because steel makes screws and steel makes nails. So as I when materials are more ductile, that's going to mean that they're going to be softer, which is usually going to imply also less stiff. So stiffness is effectively the slope of that line. So if a material is stiffer, then it will bend less when you apply the same force. So nails are softer and more flexible. So what you're going to have is a nail might look something like this, and then it breaks. And then a screw, is that right? Give me a second to remind myself here. Nope. I did it again. Brittle materials are steep. Forgive me here. Okay, so a nail is going to come out like this, and then it's going to break. A screw is going to look much more like this, and then it's going to break. Because what's going on is that nail is really ductile. So as I load it a lot in some direction somehow, right? I'm talking about tension here, but like bending a nail, all those things, it's all tension and stuff when you kind of break it down. So it's all about the same. So when I load the nail a lot and I bend it or something, it's going to deflect a lot before it like breaks. For a screw, I may be able to get a, let's see, make this proportional. This is not proportional, not to scale. Basically, a screw is going to have a super high strength before, how would I draw that? High strength. Wow, this is escaping me. Basically, screw is going to be very strong up until the point where it fails, and then it's just going to fail. It's going to probably break because they're brittle. They don't take impact load. So let's skip to the next topic about this, right? So what we care about with screws and nails is we care about what they can do, right? So a nail is very tough. A screw is not very tough. And toughness is a factor of how much energy the material can absorb before it fails. So you can have a rubber band, for example. I can stress it and load it and bend it and like do that a whole bunch, and it's going to absorb lots of my energy because I'm stressing it and then I'm releasing it. I'm stressing it and I'm releasing it. Like that's toughness. You could take a rubber ball and you could drop it off a skyscraper, and when it hits the ground, it's going to just bounce, right? That's a lot of energy being put into the ball, but it can absorb the energy and then it's still fine. Versus like glass or ceramics. If you dropped a plate off of the skyscraper, it's not a tough material. It's going to shatter when it hits the ground because impact loads put a lot of energy into a material very quickly. So toughness basically can be modeled by the area under the curve. So if this is my nail, if this is my nail and this is my screw, wow, I don't want to if I genuinely think about how this works, I'm going to stop talking, and that's dead air. So basically toughness is the area under this curve, right? Now let's talk a little bit about the curve. The area under this curve would be to here, right? So this basically is some quantifiable amount of energy the material can absorb before it fails. And the area is way larger for a nail than a screw. So that's why that matters. For the curve, what's happening here is as you load a material, there's going to be some point where, like a spring, for example, you can take a ruler and bend it, but that doesn't mean it's deformed. The material is still it has not yielded yet. When the material yields, that means it gives way to that stress and it's now permanently deformed. So somewhere in here, usually there's some point where I can load it with stress, and if I unload it, it's going to go back to its original shape. There's some point where if you hit that yield point and you go too high and then you unload the stress, you're going to, it's basically going to like move over, and you're going to get some permanent, wherever the line should go. Forgive me for that part. There's going to be some permanent deformation, right? You know that if you pull a spring too far or you push a spring too much and you bend it, it's going to be deformed that way, like a paper clip or something like that, right? So that's the stiffness, yield, toughness. The reason this is arcing over is basically what's happening is you're pulling so hard that the material starts to yield and like actually deform. And there's some point where it like technically the stress number, if you were just pulling on a thing, the stress number is going to drop off and it's going to basically get weaker right before it dies and breaks, and then it's going to break. So we're not going to get into like actual strain hardening and technical stuff here, but that's pretty much what's happening. So nails and screws. Screws are brittle. Nails are ductile. We want nails because when houses shake and earthquakes happen and things are loaded and life happens, the nails are going to be able to absorb more energy in the long term, and they're going to be able to deflect. And like you can bend a nail and then you can bend the nail back, and then you can bend the nail and then you can bend the nail back. You can do that over and over and over. Eventually it will fail, but way better than a screw. So we're going to use nails in situations where we are trying to develop, let me get rid of this here. We are trying to develop some kind of shear strength, or we are trying to hold something in position. Ideally, we are never relying on fasteners themselves in any scenario to do the work of holding material. And the reason for that is because wood combined with metal fasteners over like a long time, basically it's going to expand and contract and things are going to slide. Nails can slide out a little bit. Like, you never know what's going to happen. So you don't ever want to just hold something up and rely on hardware. Typically, you want to do something a little more permanent. But I was talking about nails versus screws. Okay, so nails are going to be where you need something to be locked in place. So if I have a wall, this is a top-down view. If I got a wall and I put a ceiling joist on top of it, the weight from the ceiling joist is going to go into the wall. Everybody's happy. And I'm going to hold the ceiling joist down with some toenails. And that's going to make that connection. Now, cross-section view, that's our ceiling joist, right? And that's our wall. Toenailing is going to do effectively that. And that is going to do a few things. So what we want to do is, because all the members in the house are connected to each other and they're actually transferring loads around in a way you wouldn't quite imagine, these nails are serving a very specific purpose. They are preventing this ceiling joist from moving this way or this way on the wall, because you are developing shear right here. And you're like, okay, well, toenails aren't ideal because they don't always go in right. And it's not as good of a connection as a full single shear connection where you've got two members and you are able to put a nail in perpendicular to their direction like that. That's a real shear connection. That's ideal. You want to do that. This is not quite that, because the nail is now going in at an angle, and that is actually reducing the effectiveness of the connection. But when you put a ceiling joist on the wall, it's not like the walls go up and then you got two top plates here. You can't just shoot a nail up like that. That's not going to work. And there's nothing keeping this thing down. So toenailing is good because you get the advantage of both the shear resistance left to right, and this thing can't come up off the wall now because there's so much friction in this nail crossing connection that you'd have to basically overcome and pull the nails back out of the wood and bend them to get that thing to come out. So there's lots of good things going on there. So that's like a nailing scenario. So why would you ever use a screw? Hashtag GRK fasteners from Mr. Jonathan. I like it. We do like GRK fasteners. Not sponsored by GRK, but they do make a nice product. And so sometimes we use them. So screws, for the structural purposes, not for like everything else. Screws they can do one of two things. So you can use small screws to basically act as temporary clamps, because a lot of framing and carpentry is, how do I get the wood to like straighten back out, or how do I get the wood to like really hold down in this one position? And sometimes you just need a temporary clamp. And if you got a whole bunch of screws, then you can just throw them in there and squeeze something together. So let's say you've got a one board and another board, and they're just like, they don't quite touch for whatever reason, and you need this thing to clamp down for like accuracy and straightness in something. So what you can do is just put a screw through here, right, and screw it in, and that's going to clamp these two together. It's going to tighten that up. Now, most people know how a screw works, right? One of the little tricks I'm going to talk about here, one of the little nuggets, is when you do this and your screw enters the first time, what's going to happen is most screws have, let's say this is an inch and a half, and you have a 3-inch screw. About 2 inches of the screw is going to be threaded, right? So you're going to get the screw in, and as soon as it enters the other piece of wood, the threads are up here, all the way down here, right? So once it enters this, the threads are engaged in this piece of wood, and the threads are going to start to engage in this piece of wood. And that's annoying. That can be problematic, because as soon as you start doing this, you want them to clamp shut, but this is not going to clamp shut until the screw, like the threads are engaging down here, and they're pulling the smooth part of the screw shaft through this piece of wood, and then that pulls this thing down. So a little trick you can do to avoid this and fix the situation is, if you don't have any, like, you don't want to pre-drill a hole for screws. That's a pain in the butt. You don't do that. For big ones maybe, but this is fine. So what you can do is you get the screw to go in most of the way, and you do not let the head of the screw get into this top piece of wood. You don't let it press into the wood. You save that for later. So you put the screw in basically up to that point, and then you back the screw out all the way out until it's not touching this member anymore. And then what happens is, when you go to put that screw back in, what you've done is you've basically made a little hole in this piece of wood. And so if you are able to temporarily push this board down and close up that gap, and then you re-enter the screw into the hole, the threads are going to be engaged in the old board, or the top board and the bottom board, and it's going to immediately hold that together. And then as soon as, of course, the screw is engaged in the bottom piece of wood, you can let go of the top piece. And then once that head comes into contact with the top board, it's going to permanently clamp that thing down, right? So that's just a little trick. You put the screw in almost all the way, you back it out, you clamp it together tight, push the screw in, get it started, and then you can clamp it all the way down. Otherwise, sometimes if you put that screw head all the way in, there's going to be a little gap left over between the boards, and that is no bueno. So that's just a little trick with screws. But for small screws, that's kind of what they're for. Now, big screws, structural screws, are, yes, I was showing you the stress strain curve where screws are more brittle. However, they make screws so strong that it's just not a problem. And so we just don't worry about it. And they're typically going to be a 3/16 or a 1/4 inch shaft diameter and bigger. These screws are usually solving a problem. They're frequently used for maybe ledgers or like holding trusses down or something. And the benefit to the screw, right, is that, well, you can install it without needing an air gun, which is kind of cool. But screws obviously resist pullout. People are like, well, screws are so good. They clamp everything. They hold everything tight together. Why don't we just frame houses with screws? And the answer is, like I said before, if your house racks and shakes and moves, you don't want all the screws failing at once and then everything comes crashing down. And also, the screws are not like the small screws. You don't want to use them in a shear situation. you want to use them in a pull-out situation. So you would use a nail here if you needed something done there, or if you were, for whatever reason, you had some piece of wood here and you needed to connect this wood to this, and the weight was being applied downwards, then okay, yes, you would screw this up. That's pretty much the only good way to do that. You can also toenail, but that's, not ideal either. So yeah, you could use screws in that scenario because the only way to resist the load is to resist by pull-out. Now, you can check these fantastical books. There are numbers that say if your screw is this diameter and you've embedded this far, like 1.5 inches into the supporting member with the screw thread, and it's this size screw and this species of wood, then you can get, it'll give you a number, like 150 pounds of pull-out resistance per inch of thread embedment. So if I put this into a 3-inch block of wood, then I have 300 pounds of pull-out resistance from this screw, where it's not going to strip itself out of this wood. That's what that means. So there's numbers for that. And that's why we use those screws. But frequently you're going to see these, like I said, on the ledgers, on things where like you really do want clamping and shear strength at the same time. That's where the structural screws are going to be super useful. So that said, that's that. All right, nail orientations. So I'm going to talk a little bit about this, and then we'll be done here. So nail orientations. There are a few different ways to nail one thing together, right? There's face nailing, which is where I have one board sitting flat. I have another board sitting flat, and I nail them together with the faces against each other. And it's going through one face and into the face of the next member. There's end nailing, which happens every time you're building a wall. You are end nailing into studs when you're building the wall because you've set out your top plate on the floor turned up and the bottom plate on the floor turned up, and you're setting the studs in between them, and then you are end nailing through each plate up into the bottom of the stud. Now that's nice because it conceals the nails. You don't see them. It's a better connection again because you got that nice clean straight shear between the two members. There's no toenail angles. Occasionally, depending on what you're building, you can't do this, and so you have to put its studs in one by one or something, and sometimes you got to like toenail in the bottom. That's fine, but that is the end nail. And next, of course, is the toenail. So the toenail is a fascinating nailing technique simply because you're able to achieve a lot of different things all at once. And again, this is, let's say, a ceiling joist on the top of a wall, 2 wall plates and a ceiling joist on top. You're going to toenail down this direction, right? And ideally, the nail is going to be fully embedded into the ceiling joist. It's not going to stick out. That would be better. But the ideal angle for doing this is going to be 30 degrees off of vertical. You don't want to go in at 45 degrees. You want this to mainly be, you want it going down more than you want it going over. And there's some reasons for that. One, because you really want the nail to penetrate into these bottom pieces of wood. And if you get too angled, I'm sure people have found, you get the nail and it starts to try to enter into this wood, and instead it'll just curve and it'll come right back up the other side. And that's a pain to pull out. So, try to keep that at a 30-degree angle. And one of the cool things that happens with a toenail connection, like I said, is with this 30-degree angle, you're getting both clamping and you're getting shear resistance. So if we just analyze this one angle, what's happening here is there is some, that's the nail, that's the angle. There is some resistance to, and that the tables in these books, they have all these numbers, right? So there's some resistance to pull out, because for this thing to pull out, what would have to happen, let's see if I can draw this, right? If this block comes up, then the nail that was in here would basically have to do that. So it's going to have to bend the nail right in there in order for that thing to come out. And instead of bending the nail like that, what it would do is it would deform the wood. It would crush the wood in that one spot, and it would be, it would bruise the wood. So you get some pull-out resistance because of that, and you get even more, of course, the more you put in different directions. Because then, as soon as you pull this up, there's no likelihood for this thing to basically also slide over and follow the nail out. If you go from both directions, then it can't move left to right at all, and that's what adds so much resistance to pull out there. So that's kind of nice. And then with shear, you are only 30 degrees off of being perfect shear going straight into the connection at a nice perpendicular angle. So you still get, I forget what the number is. Well, if it's 30, 60, 90 triangle, math? What is that? X, 2x, and x square root of 3 or something? Oh boy, it's been a minute. I think that's a 30, 60, 90 triangle. So basically, you get some, you don't get all of the shear. You don't get full shear. So if you're in your book, if your single shear connection says if you use this size nail with this side member and this full member and this, you get 200 pounds of shear strength here. But you toenail it instead, you get like some 80% or something of that value. So it's still you get most of the shear, but you also get the clamping, and it's just a nice thing, right? So that's what nails can do. And those are different nail orientations. One of the things you really want to try to avoid is you pretty much never want to, like, if you can avoid it, you don't want to screw into end grain, because end grain is extremely weak in terms of pull out resistance, right? So if you took screws and you screwed them into this, and for some reason that was being pulled down, that would be a terrible idea, and it would probably fail most likely. So the more effective way to solve this problem would be you need to introduce, like, in that case, all you're relying on is the threads of the screw and the density of the wood to hold on to that. That's all you're relying on. If you were to go underneath this and you were to nail and toenail, now you're relying on the shear strength of the nails in different directions, and that's going to resist pull out much better. So if this situation ever happened, more than likely you wouldn't rely on toenailing like this either. That just sounds like a bad idea. What you'd probably do is you'd probably get some hardware, and you'd take a metal strap and you would strap it up over the plate and you would nail it up to the plate. So you've got single shear between a metal strap and a wood piece, a block of wood. You got single shear proper right there, and then you got single shear proper right there between these two things, and that strap will just carry that weight. So that's typically what you would do. But so yeah, end grains, don't screw into those. Obviously, you nail into them when you're building walls. Just recognize that the end grain of the wood crushes easier, and that's why when you nail a stud off, you can, pretty much smack the stud around like within an inch, plus or minus half an inch. You can move the stud, and the nail is just going to kind of like follow it and hold it there. So, oh boy. Okay, Jonathan says, super helpful sistering in remodel work as old wood and new wood is warped differently. Yes, the GRK fasteners. I totally agree, Mr. Jonathan. You make an excellent point. And we have the Bright Green Observer in the chat. Aloha, Bright Green Observer. And we also got one yellow observer who likes the drawings, and blue but does not observe likes my flannel, and of course the red observer likes the regular green observer who doesn't seem to be currently chatting, but that's all right. So yeah, thank you for chatting. Yes, like the damn hit button. Yes, like the damn hit button. Subscribe and bells and belly buttons and all of those things. So yeah, I'd like to shout out those in the chat, Mr. Jonathan, right, Rockhorst, and the observers of many colors, whatever you may be. Blue but does not observe is still streaming. Oh God. Yes, Blue but does not observe is actively streaming on another channel, hosting right now an interview, I do believe. But that's how dedicated Blue but does not observe is. That's I appreciate that, Blue. Thank you. And Green Observer is here, and he is lurking. He is soaking in the knowledge that comes from the magnificent whiteboard that I haven't named yet. You know what? I got enough people in the chat here. Throw some names out here. We're gonna name the whiteboard today. We're gonna have a name for this thing before I'm done. But yeah, that's the basic premise. So there's a lot that goes into understanding how to step outside of like knowing how to frame the walls and the rafters, and you cut a bird's mouth, and you do this for the slope, and you do this for a header. Like these are all sort of skills that once you learn them one time, you just repeat to build houses. But every now and then you need to be able to put wood together in a way that solves a particular problem. And knowing how the fasteners work together, knowing how wood is meant to be installed and loaded, splitting problems like, right. So the Mr. Jonathan here got to experience what happens when you try to put like 10 nails in like 2 square inches, right? The wood doesn't like that. Bright Green Observer says, hell yeah, Green Amigo. There he is. And the Green Observer recommends a board, Boardy McBoard Face. That's a strong contender. Someone's going to have to come up with a really good name to beat that one. That is a solid one. Boardy. We might just call him Boardy for short. Boardy McBoard Face. Boardy McBoard Face. Great. Well, that's going to stay there. Unless I get a better name, but that's a strong contender. So, all righty. So, hope you guys learned something about wood and putting wood things together. I did a reasonable job explaining like stress strain diagrams. If you guys want to learn more nerdy stuff, I'm more than happy to go a little bit heavier into why the nerdy stuff. That's material science is what that is. Understanding how those things work. But yeah, I hope y'all enjoyed the show, and I definitely did not upload. Let me do this real quick here and get you guys the link in your chat, and also put in the correct overlay for when I'm exiting the live stream. If you want to learn more, and also, of course, I'll shill it here at the same time. If you want to learn more about what I'm doing here, and you've got all kinds of stuff that you want to get into. Oh, we got Starlink in the chat. Hello, Starlink. Welcome to the channel. Welcome to the nerd channel where we talk about wood. Lumberjack classes. You are correct. Bright Green Observer says Trainee McTrain Face. Oh, I get it, because we're training. We're training on how to do wood stuff here. So Trainee McTrain Face. Oh, I can see where this is going. Lumberjacky McLumberjack Face. Okay. I'm gonna let those come into the chat, and I like those names. Those are very, very creative names. It looks like all of the observers are, they're all on the same wavelength with their naming strategy. So that's great. That's good to hear. But yeah, school server is going to be www.skool.com/BFB success. And you just go there and you can watch my intro video. And if you want to join, then you can join. And we've got a community. It's not just classes, it's a community, right? So every week we have a Zoom call where we get together and we share stories about our successes, and we share projects that we're working on, and we talk about problems and solutions. And it's more about getting guys together and having a cool problem solving community. Red Observer says, go check out Sam's community at Bungalows for Bachelors. Appreciate that, Red Observer. So that's where the link is. Go check it out. And I'm going to try to consistently do these late night learnings on Thursdays here at 7:30 p.m. Central, and talk a little bit about some of the nerdy stuff. So I appreciate you guys coming in here, and I will see y'all around on the next one. I appreciate it.